Okay, let's talk about a related problem. So what happens when you have lots of threads, both reading and writing the same memory locations? So if lots of threads are all trying to read and write the same memory locations, then you're going to start to get conflicts. Let's look at an example. Suppose you had 10,000 threads that were all trying to increment 10 array elements. What's going to happen? Let's look at some code. This code's a little more complicated than we've seen in these examples before, so let me walk through it. What I'm going to do is I'm going to try writing with many threads to the same to a small number of array elements. So in this case, I'm going to write with 1 million threads into 10 array elements, and I'm going to do so in blocks of 1,000. Okay, so that's the pound defines. Got a little helper function that just prints out an array. We'll use that for debugging. And then here's the kernel we're going to use. It's a kernel because it's labeled global. It is called increment naive, and it takes a pointer to global memory, an array of integers. Each thread simply figures out what thread it is, okay, by looking at the block index, which block it is, times how many threads there are in a block, plus which thread it is inside that block. Now, what we're going to do is we're going to have every thread increment one of the elements in the array. And so to do that, we're just going to mod the thread index by the array size. Okay, so every consecutive threads are going to increment consecutive elements in the array, wrapping around at the array size. So the fact that we have 1 million threads writing into only 10 elements means that after each thread has added 1 to its corresponding element in the array, we're going to end up with 10 elements, each containing 100,000, the number 100,000. And then the code itself is simple. We have a timer class. Again, I've sort of hidden that away, so you don't have to deal with it right now. We're going to declare some host memory. We're going to declare some GPU memory. And we're going to zero out that memory. You haven't seen CUDA memset before, but it's exactly what you'd think. We're going to set all of the bytes of this device array to 0. Now we're going to launch the kernel. And I've put a timer around this because one of the things I want to show you is that atomic operations can slow things down. So here's the kernel that we called, increment naive. We're going to launch it with a number of blocks equal to the total number of threads divided by the block width, and a number of threads per block equal to the block width. And remember, these numbers initially are 1 million and 1,000. Okay, so we're going to end up launching 1,000 blocks, and we're going to pass in the device array. And then each thread is going to do its incrementing. And when it's all done, we're going to stop the timer and copy back the array using CUDA memcopy. Okay, so now we'll take that array that we just incremented and copy it back to the host. And then I hid away a little print array helper function that just prints out the contents of the array. And then I'm going to print out the amount of time taken milliseconds by this kernel that I measured with the timer. Okay, so that's the whole CUDA program. Let's compile and run it. Okay, so let's see what we've got. So 1 million threads in 1,000 blocks wrote into 10 array elements, right? So we should have, in every array element, we've done an increment operation, so we should have 100,000 in each, the number 100,000 in each of the array elements. And when we print it out, instead what we see is we've got 476. That is clearly completely wrong, and we need to figure out what happened. Let's notice, by the way, that it took about 3 milliseconds to run this code. I can run it again a few times. This time I got a different number. Okay, that's odd. Slightly different amount of time. Took slightly less time. About the same though. About 3 milliseconds. I can run it again and again, and what you're seeing is that every time I'm getting, different, seemingly random values written into each of these array elements, and it's consistently taking around 3 milliseconds, 3 to 3.2 milliseconds. So let's see what's going on. So the problem is that each of these threads is writing directly into the array and ignoring the fact that there might be many other threads doing the same thing. So if you look at this actual increment operation, every thread is reading the value at g sub I, it's adding 1 to that value, and then it's storing the result back in g sub I again. So there's a read, a modify, and a write. It's called a read, modify, write operation for that reason. So the difficulty is that there's 100,000 other threads that are also trying to read this value, compute a different value, and write the result into the same location. So in the amount of time that it takes each thread to read this value and increment it and store it back, many other threads have gotten to run at the same time, and they read the old value, the unincremented value. So since so many threads are reading the old value, the unincremented value, and adding a number, incrementing it and storing it back, you're going to get the same result written over and over and over again. You also might have older threads overwriting the results from later threads. So, it's no surprise really when you look at this code that, in fact, the numbers that we're getting in those array elements are essentially random. So what do we do about it?